So we're just going to go over some examples. It's always great to do example problems, right? Looking at different molecules and predicting their VSEPR structures. So we have COF2. How do we do this? First, we start with the number of valence electrons, right? 4 for carbon, since it's in group 4. Then we subtract off the different ligands. We have a 2-electron ligand in oxygen and a 2 1-electron ligands in fluorine. So that's going to get us 0. 0 divided by 2 gives us 0 lone pairs. We have 3 ligands total, plus 0 lone pairs is trigonal planar. And that's indeed what is the correct geometry. However, this is where some of our bond angle rules come into play. Oxygen is larger than fluorine due to the multiple bonds. That's what VSEPR says. And so you're not going to have perfect 120-degree angles here. You're going to actually have 126-degree angles for the carbon-fluorine-oxygen bonds. And then the carbon-fluorine-fluorine bond is going to be 108 degrees, significantly less than the 120 ideal geometry. So that's why I wanted to do that one. Let's look at another one here, POF3. Very similar thing. Phosphorus is in group 5. Same types of ligands. 3 fluorine 1-electron ligands, and then a 2-electron oxygen ligand. That gives you 0. And then 0 divided by 2, 0 lone pairs. 4 ligands, no lone pairs. Tetrahedral steric geometries, tetrahedral molecular geometry. But again, oxygen is bigger than fluorine. So again, you can see VSEPR. And again, oxygen is bigger because it is a multiple bond. It's a double bond versus single bond. So again, you can see how the bond angle for the fluorine phosphorus oxygen bond is bigger than 109.5. 109.5 is the ideal tetrahedral geometry. That's the angle in, for example, methane, something where it's totally symmetric, TD symmetry. But it's less than 109.5 for the phosphorus fluorine fluorine bond, and it's 103 instead. All right, so we can look at it. We can take another example here. This time we have a trimethylated phosphorus with also 2 fluorine atoms, 5 for phosphorus, 5 valence electrons, 3 for each of the methyl groups, because again, if you add a hydrogen to a methyl group, that's going to make a stable molecule methane. So that's how you know it's a 1-electron contributor here in this counting scheme. And then you have 2 1-electron ligands for fluorine. That gives you 0 lone pairs again. So 5 ligands plus 0 lone pairs, that's going to give you a trigonal bipyramidal steric geometry. And at this point, it's kind of interesting. You have 3 different options here. So you can think about this, but where you're going to want to be is this is just going to be based on sterics because the methyl groups are way bigger than the fluorine. The methyl groups contain 4 atoms versus 1 atom for fluorine, right? So the methyl groups are going to want to occupy the roomiest site. The roomiest site is in this equatorial position because you have 120-degree bond angles here versus here are right angles at 90 degrees. So what we'll soon go over and start here is that there's a number of different VSEPR exceptions, things that break the VSEPR rules. And this is, starting our further hint, which I didn't hold off too long in telling you that VSEPR is a highly flawed theory in many ways. And here's one example, okay? So if you take this indium chloride species, you say, okay, indium should have 3 valence electrons plus 2 for the charge because we're 2 minus charge, so we need 2 additional electrons. And then we're going to subtract off the 5 halogens. Those are each worth 1. That gives us 0 lone pairs. So again, just like before, we have 5 ligands plus 0 lone pairs. Should be trigonal bipyramidal. But if you take the crystal structure of this, this is square pyramidal. It's not trigonal pyramidal at all. And so, why is this? Well, if you read certain textbooks, they might say that this is due to packing effects. that somehow, because when you're in the solid state, there's some forces that cause this square pyramidal to be more favorable than trigonal bipyramidal. That is not a very precise explanation, and it's not very satisfying, okay? So it's like, oh, I got an exception, so I'm just gonna call it this thing packing effects, right? There may be forces indeed in the solid phase that are contributing to the structure, but clearly VSEPR has failed us here, okay? So we'll go over some more exceptions in the next video.